Hey, Rochelle.
Hi, Bethany.
We put a lot of time into this podcast, don't we?
Yes, and time zones. It's actually 11 p.m. right now where I am, and I'm one of those early to rise, early to bed people.
And we are not alone. We've got guest hosts and consultants and editors. We want them to be paid. And my computer recently decided to stop recording audio, so that's a bonus. And we need a little help supporting the podcast.
Yes, and we also like to do new things with the podcast, like, for instance, live shows. We've done a few in the past, a long time ago. We haven't done one for a while. We'd love to do more of these, but live shows take a different type of equipment, which we don't have a lot of. In particular, we don't have a lot of in duplicate, since we're scattered across several time zones.
I think it might be 7 time zones.
It's many. It's several, I feel, is the appropriate word.
So in order to support the podcast and do cool new things like live shows, we're doing something new on our Patreon. We're giving away, except not giving away because we're selling it. But if you support us on Patreon, we can give you awesome totes and stickers with our awesome Science for the People logo on them. Haven't you always wanted a Science for the People sticker for your forehead? And we're also doing something really special. We've got a scientist birthday club. If you support us for $5 per month or more, every year you'll get a special birthday card. It's not on your birthday. Sorry, we don't actually know when your birthday is. Instead, it's on the birthday of a scientist we think is worth knowing about. There will be custom art about that scientist and a biography introducing you to this amazing researcher who you've never heard of. And if you support us for $50, you can even get that scientist's birthday on a very sleek-looking mug.
In order to celebrate this scientist's birthday, we went to an artist that I know here in the UK, Jai Lu, and got her to create some custom art. So not only is it an unknown scientist to you, who you'll learn about, but you also get some pretty sweet custom art.
And it's a really, really cool piece of art. I'm not going to lie, it's really gorgeous. It's a great opportunity to support the podcast that you love. Or at least you're listening to it right now, which means you have to like it at least a little.
And it's almost time. Sign up by May 15th to get this year's card. If you're late, you may still get lucky. We'll keep sending them as long as supplies last. But if you definitely want one, you need to get on it right away. We're only doing a single order of these, so once they're gone, they're gone.
Now you're probably tired of this. So let's get to the science, shall we?
The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
This week on Science for the People, we're looking at a different way of producing color than you might be used to. Structural color relies on nanoscale structures to reflect particular wavelengths of light. To start things off, we'll be discussing some of the science behind naturally occurring colors and the engineering to produce manufactured ones with PhD student Victoria Hwang. After that, Maria McNamara joins us to discuss how color information is preserved in the fossil record and where the research is going. Welcome to Science for the People. I'm your host, Marian Kilgore. Joining me is Victoria Hwang, a PhD student in applied physics at Harvard University. Her research focuses on understanding the physics behind angle-independent structural colors and designing rules to create and expand the range of colors and saturation so far achieved. Applications for her research include long-lasting paints and coatings and colored electronic ink for displays. Prior to Harvard, she worked at Xerox PARC and Intellectual Ventures laboratories in the areas of colloidal materials and water sanitation. She received her bachelor's degree in chemical engineering from Princeton University. So thanks for speaking to us today.
Thank you for having me.
So we should probably start off with the basics. When I say I'm going to color something, I usually think of a paint or a dye, but you work with structural colors. So to start us off, could you explain what makes a structural color different from pigment-based colors?
Right. So structural color is a type of color that comes from the internal structure of a material. And to give you a few examples, you can see it in nature a lot. So in many species of butterflies, like the shiny blue morpho butterfly, or beetles, or peacock feathers, and actually, interestingly, all blue birds, their color comes from how light interacts with the internal features and the structure of the material. And it's important to emphasize that the internal components of the material aren't actually colored themselves, but instead the color comes from how light interferes with the arrangement of the components as a whole. And so pigment-based colors, they're very common. You see, most of the colors that you see are pigment-based, like in fabrics, clothing, paints, and also many colors in nature, like the green in trees. But these colors come from chemistry. So that means that there's some chemical pigment or a dye that absorbs all the colors that you don't see. So to give you an example, if you shine white light that is composed of red, green, and blue into a red apple, then that means that the apple skin has a molecule that absorbs all of the blue and green colors. And so the remaining red is what you see. But in structural color, there's no molecule that absorbs, but instead the internal structure of the material reflects the colors that you see and lets all the other colors pass through the material. So in the case of a blue bird that has structural blue color, the composition of the feather on the nanoscale, and nanoscale means essentially around like the size of 1,000th of a human hair. This structure reflects only the blue colors while letting the green and red pass through.
Okay. So you mentioned blue for birds and butterflies. Are there colors that are almost all structural in nature and some that are almost always pigment-based?
Yeah, and actually, so as I said before, all blue birds are structural color. And to the extent of our knowledge, we don't know of any birds that have red structural color that is angle independent. So that means that it's non-iridescent, or that the color doesn't change depending on the angle from which you look at it from. So the red birds usually have their pigment or their color from pigment, whereas blue birds have their color from structure.
You mentioned iridescent colors, so are all bird feathers that are sort of shimmery or they change color depending on the angle, are those always a structural color?
Yeah, actually, yes. Because that type of iridescent effect, you don't get it from pigment. Because again, the pigment-based color is based on absorption. So the remaining color that you do end up seeing doesn't really depend on the angle. It's an intrinsic property of the chemical components. Whereas the structure could change, depending on the color or the angle from which you look at it from. So then it makes sense that the color could also change. So in the case of peacock feathers, for instance, that you see that shimmery effect, that angle-dependent iridescence, that is definitely structural color.
So what about feathers that are more, since we're talking about birds, feathers that are more matte? Like I'm thinking of blue jays that we have in Edmonton, and they're not an iridescent sort of color. Are those more difficult to make with a structural color?
Yeah, so actually, angle-independent structural colors like the blue jay or the blue cotingas that look essentially the same as pigment-based colors, they are easier to make than the iridescent type. And I can actually tell you briefly how we do it, and it's super easy, simple, and cheap and fast. So we essentially start with something that's called a colloidal suspension, which is basically a liquid that has nanoparticles suspended in it. So milk is a typical example of a colloidal suspension. And we essentially remove all of the water in the suspension, and we end up with only the dried nanoparticles that are tightly packed. And so we can make pellets or films of these packed nanoparticles or use them as additives in a formulation. And in this way, we can create something that looks pretty much the same as paint, but without some of the disadvantages of current pigment-based colors.
So with the nanoparticles in the colors that you work on in your lab, what are those particles actually made out of?
Yeah, so you can make them out of many different materials, actually. So for example, in our research, we use a lot of plastics. So polystyrene is a type of material that we use a lot, but you can make them out of many different things. And the important property is that they interfere with light in a similar way as the birds or beetles, butterflies, as those structures do. And so the material itself is not really that important. It's more about the structure. And so other materials that are used many times are silica, for instance, which is what sand is made out of. And that's something that has also the extra advantage that is naturally sourced. So it's found naturally in many food products, like in vegetables, brown rice, oats. So these open up the field of applications in consumer products that you can wear on your skin or even in food products. And I know that, for instance, a group at Tufts University is also making structural colors with silk, which, of course, that would be safe to wear on your skin. So yeah, I guess like the variety of materials that you can use for structural color is very wide, because the material itself is not as important as the structure, because the structure is what creates the color.
Maybe let's just go back to the structural colors that form in nature. Are there naturally occurring structural colors that aren't on animals or plants, like any sort of rocks or something like that?
Yeah, so if you've ever seen an inverse opal, that's a type of very nice, also angle dependent or iridescent structural color. And you can see all the colors of the rainbow there, and they're very nice, and they're used in jewelry quite extensively. Also pearls. When you look at a pearl and there's that very nice, shiny pearlescent effect, that also comes from the internal structure of the material. And it's the reflection of the light that actually gives rise to this color. So yeah, it happens more than in plants or in animals or insects. It also happens in stones and, pearls and in many different places in nature.
So with the structural colors in nature, could you just run it past me again? So how do you take sunlight and have it reflected by a nanoscale structure in a way that makes it look so blue?
Right. Yeah. So imagine that you have a bird feather or a butterfly wing, and you take a very close-up picture of the structure. So you zoom in enough to be able to see the nanoscale features. Mm-hmm. Then we will always see that all of these structurally colored animals have an internal structure that reflects light. And the specific type of structure can vary a lot with each species, but it's often a repeating structure. Like, for example, in butterflies, it can be alternating stacked layers of chitin and air, or in plants, it can be structures of cellulose fibers, or in some birds, it can be packings of spherical particles of a material called keratin. And the key property is that the size of these features, of these particles, or the thicknesses of the alternating layers is always around the size of the wavelengths of light. So when light interacts with a material that is roughly the same size as its wavelength, then something called constructive interference happens, where one color of the light, for example, blue, constructively interferes with itself and is the only color that is reflected, whereas all other colors just pass through the material and don't come back to our eyes.
Oh, okay. So the rest of the colors are just carrying on unimpeded, and the color that you're seeing is the one that got caught up in the structure and reflected back.
Yeah, exactly.
Okay. So these structures are pretty small. How robust are they? Because, something like a bird feather is going to encounter the elements, and it's getting groomed, and it's, getting flown with. So there's a lot of abuse that they have to take.
That's right. But because these nanostructures are very, very small, so nanoscale, so that's about 1,000th of a human hair. That's very, very small. So I think that these structures are fairly robust. Birds that are playing with their feathers and grooming, they wouldn't necessarily interact or disrupt the structure on the nanoscale, but it would be more of a macroscopic effect that it would have on the feather. So yeah, the type of structure that interacts with light is so small that is actually quite robust on that scale. That would be my guess.
Fair enough. So your lab works on manufacturing colors.
Mm-hmm.
Are there manufactured structural colors already out there that people might be familiar with?
Yeah, so the research related to applications of structural color is really booming these days because, of course, color is such a fundamental part of life in everything we see and consume. So being able to create bright colors that can last longer or be less toxic than chemical dyes is really desirable in many industries. And one example is the paints or the coatings industries. So I recently learned that Lexus launched a blue car where the blue is structural. And in that case, the advantage of using structural blue coatings in cars as opposed to paint is that the color doesn't fade over time like pigment-based colors do. And another example is the field of cosmetics. Structural colors, often can have this iridescent effect that we were talking about. So that could be very interesting in, for example, nail polish or eyeshadow that changes color depending on the direction from which you look at it. That's a very novel and attractive application. And I know that, for example, L'Oreal is doing some research on this field. But also, structural color is not just about how pretty it looks, but especially in consumer products that people wear on their skin or even in food products. Lately, there's been a growing concern in the public related to the types of chemicals that are being used and their toxicity. Mm-hmm. And because structural color doesn't rely on chemical dyes, and you can make them out of materials that are non-toxic and naturally sourced, even in the field of food dyes, there's a huge market there where structural color could have a great impact.
So going back to what you had mentioned about using colloids in your lab to manufacture the colors, why is that technique in particular really useful?
Yeah, that's a great question. And so the reason why we use colloids or colloidal suspensions is because colloidal suspensions are actually quite easy to make and to purchase. But at the same time, what we need are nanoscale features in the structure. So using colloidal suspensions that are made out of nanoparticles, if we assemble these nanoparticles together, then we get the right type of size that is small enough to interact with light in this way to make structural color. So if we actually use particles that were much bigger, so if we use like spheres that were meters long, then we wouldn't be able to achieve the same effect of structural color. So it is important that the particles that we use are small in the nanoscale for the physics to be able to work.
So when you remove the water, so you'd mentioned that previously that the structures have to be small and they're repeating. How do you get everything to arrange? How do you get these nanoparticles to arrange themselves in these sort of precise structures? Rather than just randomly into a solid.
Right. So when we do that, when we start out with the colloidal suspension and remove all the water quite rapidly, the types of packings that we get are actually quite disordered. So they're not crystalline or ordered structures, but there's some degree of disorder in the structure. And that's what allows us to make angle independent or non-iridescent colors. If the structures are crystalline or highly ordered, then we would get the type of iridescent colors that we would see in the peacock feather, for example. And so those structures are actually a little harder to make. The drying process is longer usually, and it's a little bit more convoluted. But in the end, we can still get crystalline structures that have a very high order. And then in that way, we can make the iridescent type of structural color.
Oh, okay. So for the non-iridescent angle-independent colors, you're not aiming for a solid with a highly ordered structure. Like randomness is what you're looking for?
Right, yeah. It's the randomness that actually gives it this angle independence, because the structure essentially looks disordered or somewhat random, so it kind of looks the same no matter the angle from which you look at it from. But if you have a very highly ordered structure, then you can see how the structure will look different if you're looking at it from the top, whereas if you're looking at it from an angle. And so that also means that light will interfere in a different way with a crystalline structure depending on the angle, whereas in a non-iridescent structural color, light interferes in the same way from all angles if it's a disordered structure.
So in your lab, you've made various different colors using this technique. How do you control what color the nanoparticles end up reflecting?
So yeah, there are many different experimental parameters that we can tweak. And one of them, and the most important one, is the structure of the material. But there are other parameters such as the size of the particles or the layers that we're making or the type of material that we use that we can tweak and tune to achieve different types of color that actually span the whole spectrum from blue to red. So to give you an idea, if we want to make a structural color that is blue, then we would usually use smaller nanoparticles, so around a couple hundred, so around 200 nanometers in diameter. Whereas if we wanted to make red structural color, then we would use a slightly larger, around 300 nanometers in size for the particles. So by adjusting the different experimental parameters, we can actually achieve different colors.
Okay. Are some of the colors easier than others?
Yeah, blue is actually much easier than red. And that has been a very old question that our lab's previous grad student in our lab was able to answer. And the question is that in nature, it's very common to see blue birds that have structural color, but all the red birds have their color come from pigment. And we couldn't really find an example in nature, in birds or beetles or butterflies or stones in anything, where there was red structural color that was angle independent. And it's possible to see red structural color that is angle dependent, but we couldn't find angle independent structural color. And so this previous grad student, she realized that the reason for that is because whenever we try to make a red color in the lab, we always get that the blue light also gets reflected in addition to the red. So the final color ends up looking purple. And part of the reason why blue also gets reflected is due to something called multiple scattering, which means that essentially all of the light gets reflected back. So not just the red, but also the blue and some of the green. And that's currently what our research is about. We're currently trying to quantitatively and physically understand the effect of this multiple scattering in structural color and learn ways to control it. And hopefully this research will contribute to further understand the physics behind structural color and hopefully develop design rules to be able to make any color that we want.
So is that, to a certain extent, an effect of the different size of the wavelengths? Like the fact that the red has a longer wavelength means that the blue is also interacting with the particles? Yeah,
that's actually pretty much it. So because the red wavelengths are longer, it turns out that when we make structural color, there's this main color peak. So when you make a blue structural color, there's that means that there's a blue peak in the reflectance at the blue wavelengths. But it turns out that there's not only the main color peak that determines the color that you see, but there's also this secondary peak that is actually happening more at the smaller wavelengths. So that would be in the UV range. And in the case of blue structural colors, we don't see the contribution of the secondary peak because it's in the UV region and we can't see in the UV.
Okay.
But in the case of red structural color, the secondary peak is actually located in the blue. So what we end up seeing is this mixture between blue and red. And so it's purple instead of red.
Okay. One of my questions was going to be on the topic of UV and infrared. So could you make these compounds to reflect those wavelengths as well?
Yeah. So, I guess like the physics behind structural color is not limited to just the colors, right? We can also apply these principles to UV or infrared regions. So if we wanted to make a coating that is more reflected in the UV so that it doesn't heat up as much or as fast as pigment-based materials would, then in that case, using structural color could be a potential use or a potential way to get that.
That's interesting. Because, you would think if you can incorporate that into something like a fabric or something like that, then you have a good way of making UV opaque materials, which is... that's, there's many different applications that would certainly benefit from this, yeah. So when you get the color at the end of the process of evaporating the water, what sort of physical form is it in? Is it sort of a gel or is it a dry solid?
So it's usually a dry solid. So we usually make pellets or films, but we can also add them in a formulation. So make something that looks like a pigment essentially, but is not a pigment, but it's structural color. But to the eye, it could look essentially the same as paint. So yeah, there's a range of possible different formats in which structural color could be used.
So you could put these together in something that a consumer would buy in a can and apply with a brush.
Yeah, that's right, exactly. And actually, I know that there are several artists already that are using structural color for their art, and so they're using it essentially as a pigment. But they're able to achieve very fascinating color effects that they wouldn't be able to achieve with pigment-based colors. Because, if you have an iridescent type of painting or something like that, then that's a very different type of optical effect than you would get with normal paints.
So some existing paints, like glitter paints or shiny nail polishes, are those already structural colors, or are those some other sort of reflective effect going on?
So most of those are not structural colors. So what those pigments use, they usually have so they have as a base material, they have a pigment, so a chemical that absorbs some wavelengths and doesn't absorb some others. So the base material is a pigment, but they usually add additives, like, for example, metal particles or things like that reflect light in a very bright way. And so that adds this shimmering effect, or it's not quite iridescent, but more of this metallic effect that you see a lot in nail polish or in eyeshadow. So that's not quite structural color, but yeah, so they're still using pigments.
Oh, okay. And what about some other colors? Like, are white or black easier or harder to make than something like a blue pigment? Or not pigment, structural color?
Right. So, I think so white essentially means that you have all of the colors, and black means that you have no colors because all the color is absorbed. So just because if you want to make black, then you would need something that is absorbing. So you would need something that is pigment based. But there are papers out there, labs that are working on this, on how to combine absorption and structure to enhance each other. So there's actually birds of paradise, those that are very black and have this very deep absorbing black that is, you can, when you look at the bird from the front, you can't really distinguish any features because it's such an absorbing deep black. And it's been shown that the reason for that super black absorption is due to the fact that there's structure inside. And so there's this interplay between structure and absorption. The presence of the structure enhances the absorption. Oh, so yeah, you can imagine how you can use structure to enhance absorption, create deeper blacks. At the same time, you can also use structure to make brighter whites. And that is something also that many industries, especially the paints industry, is very interested in.
Okay, that's interesting. I didn't realize that that's what Birds of Paradise were doing to get those really blacks, that there was pigment and structure involved.
Right, yeah.
When you're doing these experiments to make these different colors, what do your unsuccessful experiments look like?
That's a great question. So, many times, what we struggle with is when we're making samples of structural color, it's somewhat hard to make them, look nice and homogeneous. So if we're making films, and to give you a sense of how big they are, they're probably about 1 inch squared in size, because that's about the size that we need for our experiments and to make measurements. And we get all sorts of cracking and, inhomogeneities on the surface and these things. These are more experimental challenges that come more from the engineering side of things. But yeah, so we have a lot of challenges related to that. But there's also scientific questions, like, for example, what I mentioned before about this multiple scattering that affects the structural color, and that also is related to why it's so hard to make angle-independent structural red. These are scientific questions that are still being answered, and these are questions that are actually quite hard to grasp sometimes, because it's all about how light interacts and interferes with some material. And so, yeah, it's a challenge, definitely, but it's definitely a very interesting and fun one.
What about colors that what about paints or structures that could change color? Because I have seen over the years a few paints that change color based on temperature, but they have a pretty narrow range of application. Is temperature dependence something that could be engineered into a structural color?
Yes, and actually there are several groups that are working on this type of sensing applications. So you can imagine making a film of structural color that changes based on the temperature or the humidity in the environment. So the structure itself would either, for example, if it's very humid, then the sample would absorb a lot of water and that would make it swell. So that means that it's essentially changing the structure of the material, and that leads to a color shift. So yeah, these type of applications are actually being explored quite a lot, and they're very promising.
So where do you think this technology will get used first, or at least the most uptake in the next decade or so?
Yeah, I think that the industry of coatings, car coatings, like the example of Lexus, that means that it's already being used in the industry a lot, especially for coatings in cars. And because cosmetics companies are also very interested in it, I think that there's going to be a lot of nail polish products or eyeshadows that are going to come out that have, interesting color effects. But also another cool, very interesting application is the development of electronic ink for displays, like in your Kindle. So imagine having a Kindle with all the advantages that Kindles offer for reading purposes relative to standard backlit tablets. But now the Kindle can display colors too. So that's also a very interesting application that I think is very promising. And there are companies that are working heavily on this too.
You make me so happy saying that, because I have an e-ink book reader that served me well for many years, and I'm glad that they're going to get some advantages of color displays sometime in the future.
Yeah. Definitely. I think that's going to happen soon.
What research question are you the most interested to see the answer to in the hopefully in the near future?
Yeah, so a lot of the challenges and questions that are out there are related to the engineering point of view of how can we implement this into a specific application. But, there's still many questions from a scientific perspective that haven't been answered yet. And the question that our lab is currently working on, which is the question of multiple scattering. What happens when light or the structure doesn't just reflect a certain color, but it reflects all of them, and you don't want that. How do we control that? So what parameters determine that? And how can we quantify it in a way such that we can design samples in the future to be able to, get rid of the multiple scattering, or maybe use it to our advantage to make brighter colors. So that's a topic that I'm very interested in. And then also another topic is another example that I mentioned before with the birds of paradise. I think there's a lot of interesting optical effects happening when you combine absorption and scattering, so multiple scattering, or absorption and structure. Mm-hmm. And that's a very non-trivial question, I think. There's a lot of physics to be discovered there. So I would like to work on that. And yeah, currently our research is focusing on understanding that too.
Well, great. Thanks for your time, and thanks for joining me today.
Yeah, thank you so much for having me.
You can learn more about Victoria Hwang and find links to photos of some of the colors the lab has produced, as well as more information about structural colors at our website, scienceforthepeople.ca. Just as a post-interview note for our listeners, Victoria mentioned that there is a car manufacturer out there who has been using a structural color-based paint. Lexus has put together a video of how they go about manufacturing and applying their special structural blue paint, and we have a link to it up on the website. We'll be back in a moment with more Science for the People.
Science for the People is a weekly radio show and podcast that explores everyday life from a scientific perspective. We are a member of the Skeptic Network, a collection of blogs, podcasts, and video content focusing on science and critical thinking. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to support us at Patreon, to connect with us on Facebook and Twitter, and to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. I'm your host, Marion Kilgore. Joining me is Dr. Maria McNamara from University College Cork in Ireland. She's a paleobiologist working on the preservation of soft tissues in fossil animals. Much of her current research focuses on the preservation of color in fossil insects and vertebrates, but also in fossil preservation more broadly, including the skeletal taphonomy of fossils and environmental and biological controls and preservation. So thanks for speaking to us today.
Great to be here.
I actually wanted to start with a pretty basic question about your work. What is taphonomy?
Okay, so taphonomy is the study of all of the processes that happen from the moment of death of an organism to the time which they're discovered by a paleontologist. So taphonomy covers everything from, how animals die, the killing mechanism, right through to how they're transported to the site of deposition, and everything that happens after deposition when in a sedimentary environment. So it covers burial into the Earth's crust. It includes heating up, and it includes the processes of uplift back to the Earth's surface.
So how can those events, obviously, if I understand that if an organism starts to rot a lot before it fossilizes, that would affect what sort of soft tissues preserve. But for something like bone, once it's started to fossilize, how can those affect the information that we find in the fossil afterwards?
Okay, well, in the case of bone, a lot of processes can happen to bones. So, for instance, if an animal decays, an animal might die, and its soft tissues might decay, let's say, at the side of a river. The body may be scavenged by scavengers, and those bones could get scattered, and they could get fractured and fragmented by scavengers. Then, if there's a flood event, say if a nearby river floods, those bones could get entrained into the river. They'll get broken around. They could get abraded, fractured even more, and they could get deposited across a wide environment. Once those bones are buried, they can be affected by fluids moving through those buried sediments. So our Earth's crust is full of hot fluids, and these have lots of salts dissolved in them. So if they encounter biological material like a bone, they can actually dissolve the minerals of the bone. They can completely destroy the bone structure, leaving you without just a mold of the bone, an external impression. Or sometimes those minerals can, those salts in those hot fluids can actually reprecipitate, recrystallize, and they can actually preserve some of the biological structures, but in a completely different mineral. So, even hard materials like bones and teeth, they can be affected by these fossilization processes.
And the reason I wanted to talk to you was that you've worked on the preservation of color in the fossil record. And when I was talking to my previous guest about feathers and her work replicating or creating structural colors in the lab, I started thinking about feathers on dinosaurs and whether it was possible at all that we could learn color information from the structure of feathers. So do those sorts of nanostructures survive fossilization?
Okay, so in terms of structural colours in feathers, they're generated in two ways. You can get structural colours, iridescent structural colours, which are generated by layers of melanin granules. So in modern birds, if these little microscopic granules of the pigment melanin, if they line up in a very ordered way, they can effectively act as a mirror and reflecting light. And multiple layers of these melanin granules will result in more reflection and brighter colours. So that's one way that modern birds can generate structural colours. Another way, and these do preserve in fossils. We have reports of fossil feathers which seem to preserve these very ordered arrangements of melanin granules, or melanosomes as they're called. The second way in which feathers can generate structural colours is using what we call quasi-ordered nanostructures, formed by not by the melanosomes, but by the keratin matrix of the feather. And various modern birds do this. A blue jay, for instance, the blue colour is generated by these, a squiggly mass of keratin, which is actually quasi-ordered. It's ordered at very short nanometer scales. And these can scatter light in a regular fashion, typically producing blue colours. So that's the second way that birds can produce colours. But unfortunately, the keratin matrix doesn't preserve so well, and actually preservation of keratin is very controversial in fossils. There's still no general consensus as to whether keratin can preserve, and so these quasi-ordered networks have not been reported yet in fossils. It's something which my group is working on at the moment, but we have no answers yet.
So then, the process of preserving a feather as a fossil, the minerals that do that don't obscure the melanin-based structures, or at least not as badly as they would with the keratin?
Right, okay. Well, the vast majority of fossil feathers are not preserved in minerals at all. They're still preserved as organic remains. So they're still preserved as carbon-based molecules. Now, the carbon-based molecules in which they're preserved are not necessarily identical to the original composition. We're not saying that just because your fossil is primarily composed of carbon doesn't mean that all the original biomolecules are preserved, such as keratin. We know they're not. We know from various experiments that different groups have done over the last 20 years that when fossil insects and leaves and feathers, when they're preserved in rocks or as organic remains, the organic molecules, the lipids, the fats, they actually combine, they join up during fossilization to form big polymers. And these polymers obviously have a very different composition to the original tissue. So most feathers are preserved as these carbon-based remains. And we're only now, trying to pick apart the exact composition of the organic remains of fossil feathers.
Oh, I guess I hadn't put two and two together that they were actually still carbon-based molecules. I'm just so used to the sort of pop-sci idea of a fossil that their, minerals went in and replaced the structures that were originally there.
So that applies to very decay-prone soft tissues, things like muscle or skin, for instance. These are typically preserved in fossils as mineralized remains, and the reasons for this aren't fully understood. But we think it's probably because these tissues are so decay-prone; they decay very rapidly. Within hours, days, or a couple of weeks. Their tissue surfaces are very reactive, and when they start to decay, they become very negatively charged, and these will bind any mineral ions that are present in the medium. And so, for instance, calcium ions can bind to the surface, and then that can trigger precipitation of calcium minerals, such as calcium phosphate. And so most skin and muscle in the fossil record is preserved actually in calcium phosphate. But tissues that don't decay very quickly, they don't generate the same very steep geochemical gradients. You don't get the same fluxes, movement of mineral ions around very decay-resistant tissues. So decay-resistant tissues like leaves and insect cuticle and feathers, these are usually preserved just as degraded and polymerized remains of the original molecules.
When you find a fossil with, say a beetle with the exoskeleton or a feather, actually, let's just go back to the beetles, because there are some fossil beetles where the fossil itself has a visible iridescent sort of color. Mm-hmm. So does that reflect what it would have been in life, or has that been modified by the process of polymerization and fossilization?
So, very good question. So, myself and some colleagues, we did some work on these metallic fossil beetles a number of years ago, about 5 years ago, and we looked at, I forget now exactly, but we looked at 600-700 specimens from different fossil localities all over the world, and we were allowed to take samples from some of these fossil beetles, very small samples, you're 0.5 millimeter in size. And we analysed them with electron microscopes. And we found that they preserve layered structures in the very outermost part of the cuticle called the epicuticle. And these very finely layered structures, they're tiny. They're, you get 10 of these layers in a micron, and a micron is 100 times thinner than a human hair. So you're talking about really tiny structures. But incidentally, these little layers that we found, they are identical to what we see in modern insects with metallic colors. And we were able to do some computer modeling, which showed that these layers in the fossils, they were capable of producing visible light. So they were scattering visible wavelengths. So they are proper photonic structures. They are, physical structures that are interacting with light to produce color. But the problem was our models showed that the colors that they should be producing are not the colors that they're actually producing. When we try to work out what colors a structure should produce, it's dependent on both the spacing of the layers and also on the chemistry of the material, on its refractive index, which is a measure of how much it bends light. So for instance, we're all familiar with the fact that air and water bend light differently, because, if you have a straw in a glass of water that's half full, the straw appears to have a kink where the air and water meet. Mm-hmm. That's because air and water bend light differently. So that's how these structures are actually scattering light, because the different layers have different chemistries and bend light in different ways. But our models basically told us that something has changed about these fossil structures. Because they're not producing the colors now that they would have had when they were alive millions of years ago. So we did some experiments whereby we effectively, simulated the fossilization process in the lab. We took some modern beetles which have these layers in their cuticles and which produce these lovely metallic colors. And we took these modern beetles and we decayed them. And we heated them up to high temperatures and pressures, like what you'd get during burial in the Earth's crust. And during our experiments, our beetles changed colour. And we analysed the cuticles to try and understand why. And we found that the layers were getting thinner, which was resulting in a blue shift. The colours were being blue shifted to shorter wavelengths. But also the chemistry of the cuticles was changing. So this was changing the refractive index. So it was changing how the cuticles are actually bending light. So, when we apply these results to our fossils, our fossils have all experienced some degree of maturation. They've all experienced, chemical change. And they've just, because of the fact, they're fossils and they've been buried in sediments, they've probably been subjected to some compression as well. So in the fossils, the reasons why we don't see the original colors are because of a combination of the physical structure changing, those layers are changing in thickness, but also because their chemistry is different. So they're bending light differently. So when we see these lovely metallic colors in fossil insects, we can say for sure these species were generating colors to use for signaling, possibly as, mating displays, but we can't reconstruct the exact color unless you have a very good idea of how much those fossils have been buried during the fossilization process.
So the information about the area where they came from and what was found around them, you would need that information as well before you could try and reconstruct their actual color in life?
Exactly. You'd need to have some handle on it. And even then, I'm not sure how precise we can actually be, because, we conduct our experiments over a matter of hours rather than millions of years. We're because when we do the experiments, the chemicals we see in the cuticles look pretty similar to what we see in the fossils. But there's always a chance that they're not a perfect match. There's always a chance that something funny happened in a particular fossil biota that we can't constrain or that we don't fully understand. So I would say with the insects, we can probably get a good handle for the amount of relative change between different fossil locations. But I don't know if we could really get the specific colours. Not yet, anyway.
So with there have been papers in the last 10 or so years looking at melanin as a pigment in various fossils and trying to reconstruct the patterns that they would have shown in life. How do you know that the pigment that's getting evaluated was actually part of the animal, or whether it was just sort of an artifact of fossilization? I guess, how do you know what you don't, or how do you figure out what you don't know about the fossil?
Right, yeah, that's a good question. So, I mean, when we think about pigments, the most common pigment that has been reported in fossils, the only pigment that's been reported in vertebrate fossils is melanin. Traces of these little melanin granules or melanosomes. And the thing about melanin is that it has a rather unique chemistry. And so there are methods that we can use to look for diagnostic fragments of the melanin molecule in fossils. And there's a technique that my group is using, and it was developed by a group in Japan to actually characterize melanin in modern animal tissues. And so this technique, it's a chemical assay that basically breaks melanin down into unique fragments that cannot, as far as we understand, can't be produced by any other process. So if we apply this technique to look at fossils, well then, to the best of our knowledge, if we find these molecular markers, these little fragments of melanin, well then it means that there was melanin present. Because as far as we know, these molecular fragments can't be produced by any other method. So in terms of chemistry, that's a pretty good method. That's a direct method for measuring melanin. There are also other chemical techniques which you can use to look for proteins, for instance, which would suggest the presence of melanin but wouldn't be as definitive. And finally, you can test for presence of melanin using morphological methods, so by looking for more physical remains of those little melanin granules. But the problem is those look a bit like bacteria in terms of their size and shape. So finding those granules on its own isn't enough to prove that melanin was present. And that's all very well and good. And, we can study melanin because it seems to be preserved in a lot of fossils. But maybe what we're not really considering is whether other pigments were present, whether other pigments like carotenoids or pterins. And we know in modern birds, for instance, many birds have melanin in their feathers, but their colours aren't black or brown. The melanin often is an accessory pigment, that there's some other pigment that's dominant. So, we've got to start looking at, remains of other pigments in feathers. And again, this is something which my group is looking at the moment.
So things like flamingos that get some of their pigment from their diet wouldn't necessarily preserve.
Oh, well, see, the thing is nobody's actually looking. There's a researcher at the American Museum of Natural History, Paul Nassenbean. He did he published a paper a year or two ago looking for evidence of carotenoids, but he didn't find any. But I definitely think it's worth putting more time and resources into trying to come up with creative ways of, well, how can we test whether these other pigments might be present? So I think we just need to start looking for them. I'd be very surprised if we couldn't find evidence of any other pigment in fossil feathers. Some fossil feathers are extremely well preserved, especially specimens in amber, for instance.
When the research progresses enough that we can reconstruct confidently the colors of some of these fossilized animals, what sorts of things might we be able to tell about the environment they lived in or their behavior?
Yeah, so the color is so interesting because animals use it for communication. It's one of the primary functions of color in animals. And, we can start to look at, you can look at the individual species and you can maybe work out things like whether the environment was a shady environment or an open environment. But to be honest, I don't think that we're really able to characterize that accurately. If you see striking patterning, you can make some guesses, educated guesses as to whether the pattern was functioning in camouflage or in mating displays based on the nature of the pattern and the color type and where it's occurring on the body. But I actually think, I think personally, I've had enough of just painting pretty pictures of fossils. And I actually think that there are some much more important and much more fundamental questions that we should be asking about color. I think, for instance, in terms of visual coloration, we should be asking ourselves, what are the driving forces in evolutionary terms? What are the evolutionary drivers that are controlling color change in animals? In terms of signaling, is color primarily driven by natural selection? So the need to hide yourself from predators, for instance, or to frighten away predators? Or is it driven by sexual selection? Is it driven more by, the need to prove yourself fit to a mate? Because we know these two forces often act in opposition. So I think in broader evolutionary terms through deep time, I think we should be looking at, what evolutionary forces are coming into play. And does it vary across different species? Does it vary across different types of animals? And does it vary through time? Because that would be really neat to reconstruct. I also think we should be looking kind of more broadly at the broader functions of colour, because there's some suggestions out there that, coloration in animals, its original function was not for visual signalling, but that it instead had some other physiological functions. Pigments have physiological functions, and that, over time, these pigments were co-opted. They were used for another purpose. And I think it would be very useful to try and test that hypothesis using fossils, to try and understand, is it true and is it accurate? And if it is, well then when and where did the functions of colour start to change? And what environmental processes were happening that caused a fundamental shift in the function of colour in our bodies? So I think there are some really big, deep questions that we could try to answer using the fossil record.
Yeah, that would be really interesting if we could start to tease apart that sort of question. Well, I know you have to run, so thank you very much for joining me.
Thank you.
You can learn more about Dr. McNamara and find links to her papers and work on fossilized color at our website, scienceforthepeople.ca. There you can also find past episodes, our social media links, and learn how to support the show. Thanks for listening, and we hope you'll join us next time on Science for the People.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network, a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.